So the next chi-square test is, again, it's a chi-square. So we're using the same test statistic, same parts. It's just a different type of test. When do we use this one? We use this one, still categorical. We're still looking at categorical. But we use this one when we want to test for a relationship or an association or to see if two things are dependent or independent. Okay? So it'll be pretty obvious when they want you to use this one because they'll say, is there an association between these two categorical variables, whatever they are? Are these two independent of each other based on the data? Then they want us to use this. This is probably the easiest one to tell when we use this one because based off the question, there'll always be um, the words independence or association in there. Okay. So our hypotheses are one of two. One of two. We can say no, the null is always going to be no. There is no association between the two variables. And the alternative is yes, there is. Or if they're asking about independence, you say yes, they are independent. Remember, independent means there's no association between them. There's nothing related. Okay? And the alternative is the variables are not independent, meaning there is an association. So really these things say the same thing. Both of these nulls say exactly the same thing, just different ways of saying it. Okay, and same thing with these guys. Okay, they're just worded differently. So it just depends on what they use in the question. If they use the word association, these are the ones you're going to use. If they use the word independence or independent, those are the ones you're going to use. But essentially, they say the same thing. Okay, degrees of freedom is going to be a little different. Degrees of freedom. We'll talk about we'll skip degrees of freedom for right now. The conditions are the same as goodness of fit, so that's we don't have to really talk about that. Formula is the same. Expected counts is different. Expected counts, we use this formula here. Row total times column total divided by grand total or table total. Okay, so the problem we're going to do, this is how we calculate our expected counts. Okay, differently than goodness of fit. Okay, all right, so let's look at the first example here. Okay, so we have a two-way table. All right, we have color choice, categories of color choice, and we have rows, which happen to be grades, grade 11 or grade 1 and grade 2, first grade and 10th grade. Okay, so here we have tables, but we're going to see two-way tables, not like the table we saw last time. Let me show you. Let me show you the difference. So the tables we saw last time were not two-way tables. They weren't two-way tables, so start with the first table. They were not two-way tables because there's only one variable here. What's the only variable here? Color, that's it. These guys over here are not variables. That's just the observed and the expected, right? Same thing down here with the astrology signs, right? There's only one variable here. Signs, that's it, right? These guys are the expected and the observed. Today, there are two variables. What are the two variables? Grade and color choice. Yeah, grade and color choice. So it's a two-way table, okay? So when there's a two-way table, we're not going to use goodness of fit. That's another way to tell. When do we use goodness of fit? Not when we have a two-way table. Okay, two-way tables are two categorical variables. Data can be arranged in columns, in rows and column format called a two-way table. Okay, so we want to see, the question says, is there an association? Is there an association between color choice and the grade they're in, right? I'm guessing this is favorite color choice, and grade they're in. Is there something there? Is there a connection? If you tell me someone's in first grade, is that going to lead me to, oh, I kind of know, I know what their favorite color is going to be, or more likely to know their favorite color, right? Or if you tell me their favorite color is yellow, is that going to lead me to say, oh, they're more likely a second grader than a first grader? That's what we're doing here. We're looking for an association. Okay? So these are all of the observed, right? There was 30 first graders, 13 of them liked blue, 7 liked green, 8 red, 2 yellow. And then there were 33 second graders, 11 liked blue, 10 liked green, 6 liked red, 5 liked yellow. Okay, and then there's totals, right? If there isn't totals, we can create the totals. Sometimes these totals won't be there, so you might need to create those on your own, but they're not that bad. Okay? Okay, so expected counts. So like we did on the last one, we're going to do calculations first. Okay, so I'm going to do calculations just because it comes from a table. It's easier just to deal with the table now, then come back to it. Okay, so expected counts. Each cell we have, in this case, we have, let me highlight them. We have 1, 2, 3, 4, 5, 6, 7, 8 cells. The rest of them are totals or titles, right? Though the ones that I highlighted, the 4 that I highlighted, are the only ones that are the expected value, or no, sorry, observed value. So all of those yellows are observed value. We need to we need to create expected. How many would I expect? How many first graders should I expect to like blue, to like green, to like red, to like yellow? Okay, so how to calculate those? Right here. When we have a two-way table, expected count, row total times column total divided by grand total. Okay, so I'm going to do the expected counts for blue, first grade blue. First grade blue. Okay, so first grade blue, row total for first grade is 30. So it's going to be 30 times column total for blue is 24. Divided by grand total. Grand total is always bottom right corner, 63. So I'm going to crunch those numbers. 30 times 24 divided by 63, and you get, which 62 where?
Because the second graders, they added up.
The second graders, they didn't add up correctly? Let's see, 11, let's see. 21 plus 11 is 32? Okay, so let's change that. Yep. Okay, so that means grand, so we get 62 here. Let's make sure the bottom total adds up too. 62? Okay, we're good then. Yep, must have been typo. Yep, we're good then. Okay, so let me change this bottom one to 62. Okay, so 30 times 24 divided by 62, and I get 11.613. 11.613. So I'm going to put that in here. 11.613. That is my expected. That's what I would expect to see. I would expect around 11 or 12 first graders to like blue. Okay. Now let me do expected counts for green first graders. So still first, green. So same row, so 30, different column now, that's 17, divided by 62. And I get 8.226. Okay? You only need to show the first two. They got the idea of how you're doing it. So the rest you can do on your own. So what I want you to do right now is come up with the expected for the rest of them. Okay? I'll give you a few minutes. Come up with what the expected number is going to be for the rest, the 6 cells that I haven't labeled yet. Okay, so which one? Okay, so now we got the expected counts, we have the observed, we started with the observed. Now chi-square, right? Each of these 8 cells is going to give me a chi-square statistic, and then I'm going to add them all together. Okay, so let's do the first two. So blue first grade, the observed is 13, the expected is 11.613. I'm going to square that, and then I'm going to divide by the expected. The next one is green, first grade, observed minus expected, squared, over expected. Oops. Plus dot, 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 and then the last one is observed. Yellow second graders would be the last one if I was to go in order. .613 squared over 3.613. Okay, that's the work I need to show. And like I said, you can crunch the numbers. It's just 8 different numbers. It'll take you a little bit of time, but you can do it with any regular calculator. But, oops, actually I don't need this guy because I already have the plus signs. Okay, so I'm going to teach you how to use the calculator to quickly crunch those numbers. Okay, so because the calculator, again, we'll do it, but it's not the same as yesterday. Yesterday's chi-square test was a little different. Okay, so here we go. Okay, so first thing we need is the observed and the expected. Observed and the expected. We're not going to use, because watch, we're going to use a different test. I'll go to the test first. If we go to stat test, there's 2 chi-square tests. There's one that says GOF and there's one that doesn't say GOF. The GOF yesterday we used, right? We're not going to use that one today because this is not a goodness of fit test. We're going to use the one right above it, okay? But you notice for the observed and the expected, it doesn't say L1 and L2 because we're not going to use L1 and L2. L1 and L2 are not for two-way tables. If we're going to use a two-way table, we have to use what's called a matrix. Okay, we have to use the matrix. A matrix is a two-way table or three-way table. It's tables in a calculator. Okay, so you're going to go to the matrix button, which is right below the math button. If you look at the math button on the left-hand column, 4 down, you're going to go to the matrix button. And you'll get these. Okay, we're going to need to edit one. Just like you edit a list, you're going to edit a matrix. So you're going to edit the first one, A, matrix A. You're going to edit. And then you're going to tell the calculator how big of a table do you need. How big of a table do we need? Just like when you're typing up a paper and you need to make a table on a Google Doc. How do you build a table on a Google Doc? How many rows and how many columns, right? You start with that and then it gives you something and then you can use it. So how many rows do we have? 2 rows. Okay. How many columns do we have? 4 columns for a total of 8 cells, right? And then we hit enter. Then it gives us a 2x4, right? So now we're going to put the numbers in the order the way they appear on the table. So 13, oops, enter, 7, enter, 8 and 2, 11, 10, 6, and 5. Okay, there's our table. The top row is first grade, the bottom row is second grade, and then we have blue, green, red, yellow. Okay, now we're going to go back. We're going to go back to, we don't have to put expected. I'm going to show you a little trick. Go back to the test that we're going to use, which is chi-square, not goodness of fit. So my observed now are in matrix A. Expected, don't worry about that. Go down to calculate or draw, it doesn't matter, but I'm going to go calculate. There's my chi-square there. That's my chi-square statistic right there. So let me write that down first. Chi-square is 2.2053. That's my chi-square statistic. When I add up all of those chi-squareds for each of those 8 cells, it's going to give me 2.205285, blah, blah, blah. And then it also gives me a p-value. Right below its p-value. So let me write that down. The p-value is 0.52 or 309. Okay. And then degrees of freedom are 3. I'll show you how they got 3. I didn't tell you how they got 3, but I'll show you. It's really easy. Okay. Okay.
Question.
Uh-huh.
For the last one, you told us that we need to include how we got the DF. So if we do the calculator this way, do we also need to include the math that we do, or can we just put the number?
There is some math. It's really easy math. I'll tell you in a second. Yeah. Yeah. When we go to test statistic, I'll show you what it is. It's really simple. But yeah, I would just in case. But it's not the worst thing in the world if you didn't. It's not the biggest mistake. So yeah. Okay. Okay. So how did they do that without the observed, or sorry, without the expected? Because you need expected, right? Well, go back to your matrix. You want to see a magic trick? Go back to your matrix. Now there should be a B the exact same size as A. Go down to B, or sorry, no, go to edit. Now go down to B. Enter. Those are all of our expecteds. Okay, it calculates the expecteds for you. Okay. Okay. So, calculator. That's it for the calculator part right now. Okay. So let's go back now. Let's go back into the other parts now. Okay. So we know what our p-value is. We know what our chi-square is going to be. We know degrees of freedom. Okay, so let's go back to start with population parameter. Population parameter. Okay. So we have, how many populations do we have? Who are they? First graders and second graders, right? They each have separate colors, right? They each have a color, but we have first grade. So we can say P1 and P2. Okay, so we would say the true distribution of proportions of favorite colors for first graders, or color choice. Probably should put color choice instead because that's the same wording they used. Same thing, but color choice. Okay, so P2 is going to be exactly the same thing, but instead of first graders, it's going to say second graders. Okay. You want to include the word distribution because it's more than one color. If it was just one color, we would just say the true proportion of that color. But it's not, it's the distribution because there's many, many colors that go with it. Okay. Okay. Hypotheses. Scroll up a little bit. Hypotheses is going to be in words, one or the other. If they use the word association, use the first two hypotheses. If they use the word independent or dependent, use the bottom. They didn't use that word, so we can pick each one we want. We can pick which one we want. Okay? So I'm going to pick the first one. There is no association. So there is no association between grade and color choice. Okay. The alternative is that there is an association between grade and color choice. There is an association between grade and color choice. Okay. So if we were going to use independent instead of association, we would say that if there is no association, they're independent. So we would say color choice and grade are independent for the null, and dependent for the alternative. Okay. All right. Alpha level, they didn't give us one, so we'll use 5%. Okay. Assumptions, conditions. I narrowed it down to 2 this time because we talked about yesterday 2 and 3. If it passes 2, then 3 is okay. If it doesn't pass 2, we got to include 3. Okay. So SRS. So when we're talking about an SRS, what are we talking about? A simple random sample of what? Okay. So we're talking about a random sample of who or what? First and second graders, right? That's what we're looking at. We don't know that. They didn't tell us that. So we can't say stated. Stated would be wrong. We also can't say that we also can't say that it's a convenience sample or it was done incorrectly because we don't know how they did it, right? So for this one right here, we can't really say anything but not stated. We don't know. We just don't know. I can't say anything other than that. I can't question their method. We questioned the method the last time because I told you my method, right? You knew my method. Here, we don't know their method, so we can't question it. We just say it's not stated. We don't know. Okay? Expected counts. All expected counts greater than 5. So let's scroll back up to the table. No. We have 1, 2, 3, 4, 5, 6 out of 8. 6 out of 8. Which is 75%. Okay, so let's go to the third one. 80% of expected counts greater than or equal to 1. Well, they're all bigger than 1. So we would say yes. 8 out of 8 equals 100%. Okay, when you're dealing with low numbers, with low totals, that might happen. Okay, didn't happen yesterday because we were talking about hundreds of people or hundreds of CEOs, right? But today we're talking about 60, 62. Okay. All right. Formulas used. Formulas used. First of all, we use chi-square, which is observed minus expected squared over expected. Degrees of freedom. How do you calculate degrees of freedom for a two-way table? This is what you do. You do row minus 1 times column minus 1. So whatever the rows are, minus 1. Whatever the columns are, minus 1. Multiply them together, you get your answer. Okay. So we had 2 rows. So 1 times 1, 2, 3, 4 columns. So we had a degrees of freedom of 3. That's how we got 3 as degrees of freedom. Okay. Another way, a college professor showed me this. I'd never seen this way before. An easy way to do it on a two-way table is to cross out the first line, the first row, cross out the first column. How many cells are left? 3. That's another way to do it. It's a quick way to do it. So on a multiple choice, if they're asking you that, I'd probably do that, right? You can only do it for a two-way table. It doesn't work for goodness of fit. Goodness of fit are not two-way tables. You cross out the first row. You cross out the first column. How many cells are left? That's your degrees of freedom. Okay. Otherwise, it's row minus 1, column minus 1, multiply them together. All right, last part, conclusion. Conclusion. Okay. Since p-value in this case was 0.5309, is greater than alpha level, which is 0.05, we fail to reject the null hypothesis. Okay. Therefore, we lack sufficient or significant evidence to show what? How do we say this in context? To show there is an association between grade and color choice. Okay. We don't have enough information to say there is an association. We don't know. So that means they're independent. They're independent of each other. Knowing someone's grade and knowing what color they prefer, they're independent of each other. We can't tell anything about it. We don't have enough evidence to say there is no association, that they're independent, or that they're independent. Wait. If we lack sufficient evidence to show there's an association, that means they're not associated, which means they are dependent. Okay. So that is the next, that is for goodness, or not goodness of fit, it's for tests for association independence. Okay, that's for test of association and independence. The last one, the last chi-square, is homogeneity of populations. It sounds like a really complicated thing, but what is homogeneity? What does that mean? Sameness, right? For lack of a better term, sameness. If a population is homogeneous, they're similar in one aspect or another, right? So we're looking at two different populations and seeing if they're the same in a certain characteristic, right? That's the last one, which is very much related to this. It's another two-way table type of thing. When we start doing it tomorrow, you're going to be like, oh, this is like what we did yesterday. Yes, it is. Conclusion will be a little different, but um, and the hypotheses will be different, but besides that, it'll be very similar. Okay. Yeah. Yeah. Okay. Um, any questions